So what we've talked about so far is direct proportion. In direct proportion, when one number gets larger, the other number gets larger. So kind of like what we had with the slopes. If we have a 2 to 3 slope factor, a rise of 2 for a run of 3, well, the larger the run gets, the larger the rise has to get. That is a direct proportion. Most of our aspect ratios, our tapers and stuff like that, are direct proportions. What we're going to look at today is something called an inverse proportion. In an inverse proportion, when one number gets larger, the other has to get smaller in a related manner. For example, in electricity, your voltage is equal to your current times your resistance. So if we have a 12-volt system, that means the voltage is always 12 volts. This is like a car system. If the current is to be 3 amps, well, then the resistance has to be, 12 volts equals 3 times R. What's R going to end up being? You divide both sides by 3 to get R equals 4, right? You'd have 4 ohms of resistance. But let's say you want that current to go up to 6 amps. Well, the voltage is still 12. The current goes up to 6 amps. The resistance has to go down to 2 ohms. As the current needs to get larger, the resistance has to get smaller. And vice versa. If the current needs to get smaller, the resistance has to get larger. That is an inverse relationship. Now, you guys aren't so much concerned about electricity as you are about the mechanical side of things. So let's take a look at some more of my beautiful drawings. We have 2 gears meshing together. Of course, this one has 12 teeth and this one has 8 teeth. If the 12-tooth gear is operating at 480 RPM, how fast does the 8-tooth gear have to go? Is it going to be going faster or slower? It's going to be going faster. It has less teeth. It's smaller, so therefore it has to have more RPMs, faster. The way to think about it is the number of teeth that go through here where the gears mesh has to be the same from each gear. Well, this first gear, the 12-tooth gear, turns around 1 complete revolution. There are 12 teeth that have gone through there. Well, that 8-tooth gear has to turn around 1.5 times to get 12 teeth through there. So it has to turn faster. It has to have more RPM because it has less teeth. There are a couple of ways to do this. There is something called an inverse proportion. And in an inverse proportion, what they do is they actually flip over one of the ratios. You have a ratio of teeth of 12 to 8. The 480 RPMs goes with the 12-tooth gear. But because this is an inverse relationship, we put the 480 down here. Even though it goes with the 12, we flip. This proportion gets flipped over because it's inverse. To me, that's confusing as heck. What you're going to do is you're going to cross multiply and divide here and get that this has to be 720 RPM. To me, the easier way to deal with an inverse proportion is not to set up a proportion. Just think of it as an inverse variation or inverse relationship. And in an inverse relationship, what we're dealing with, is a constant product. In this direct relationship we had up here, in a direct relationship, it's a constant ratio. That's why the proportion worked out so well, because the ratio of rise to run is 2 to 3. Well, the ratio over here of rise to run is also going to be 2 to 3. So let's say that this is 24 inches. The 24 inches goes on bottom because it's going to have the same ratio. This rise to that run is going to have the same ratio as the 2 to 3 rise to run. That's why the proportion works well. But this isn't a constant ratio. This is a constant product. So an actual proportion can be used if you remember to flip one of the ratios over. But like I said, to me that's confusing. It's easier just to run it as, hey, the number of teeth that go through here per minute has to be the same for each gear. The number of teeth from this gear is equal to its size times its speed. So in this case, size times RPM. 12 times 480. That has to equal the size of the other gear times its RPM. Now it's still going to be a multiply and divide, it's just not cross multiply and divide. You're going to do the 12 times 480 and then divided by 8, which will give you 720, which is what we had up there. Same will work with pulleys. Let's say I have a 4-inch pulley turning a 10-inch pulley. And let's say that the 4-inch pulley is operating at 200 RPM. I want to find the RPM for the 10-inch pulley. Well, it's size times speed. So 4 times 200 equals 10 times X, blank, whatever you want to call it. So it's going to be 4 times 200 is 800. Divided by 10 is 80 RPM. Make sense? This applies to anything that would be an inverse relationship. For example, let's say you're a sump pump. I used to do a lot of construction. You'd dig a pit or a foundation or whatever, and it would rain over the weekend. You'd come back on Monday and it's full of water. So you throw your pump in there and you pump it out. Well, let's say I have a pump that is capable of pumping 9 CFM. CFM stands for cubic feet per minute. And with that pump, it takes 6 hours to empty that. Well, let's say that I then get it pumped out. I decide to let it dry out overnight, go to a different job site. It rains overnight again. I come back and it's full of water again. This time I don't want to wait 6 hours, so I go borrow a bigger pump. It's 12 CFM. How long is it going to take? Well, again, it is size times speed, or speed times rate times time. Same type of deal. So I have 9 CFM times 6 hours. That's going to equal 12 CFM times blank hours, or X hours. 9 times 6 is 54. Divided by 12 is 4.5. So it's going to take 4.5, or 4.5 hours. Make sense? Okay. Well, let's get a little more complicated. Now let's have you guys try one, actually. Let's do a 3-inch turning a 15-inch pulley. Now let's say the 3-inch pulley is turning at 1,000 RPM. How fast is the 15-incher going to turn? So yeah, it's going to be 3 inches times 1,000 RPMs equals 15 inches times blank. So this will be 3,000 divided by 15 is 200. So 200 RPM. Now I want you to try this one. So I had a 4-inch pulley turning a 16-inch pulley. Then a 3-inch pulley going to a 5-inch pulley. And this is turning at 1,200 RPM. I want to know how fast the 5-inch pulley is turning. Go ahead and give that a shot. See if you can figure. Now, I will tell you the mistake that most people make will be in the second step here. So anyway, we have 4 times 1,200 equals 16 times blank. If you multiply that out and divide, it's 300 RPM at the 16-inch pulley. How do we find out the RPM at the 3-inch pulley? No. They're not connected by a pulley, are they? They're on the same shaft, aren't they? If they're on the same shaft, they have to turn the same speed. That's where most people make the mistake. They'll start doing, 16 times 300 equals 3 times, no. They're on the same shaft. They're connected. They have to be going the same speed. So that is now 3 times 300 equals 5 times blank. And yes, that would come out to 180. I threw that out there on purpose because most people miss that and they start cranking through the formula. When you're looking at these, make sure you ask yourself, what has to be going the same speed? For tomorrow, a couple things for you guys to play with. In the book packet that I gave you on page 236, it is 8 through 10. There's only 3 of those. Then in the other packet, it's 40 through 41, and probably can work on 46 through 72. So that'll be enough to keep you busy for a while.